Great. I'm the last talk of the day, so thanks for surviving this long and for coming here. So my talk today will be about how do we go and think about applying machine learning to kind of high-stakes prediction problems. And in particular, we'll be talking about applying machine learning to legal domain, where we really want to make sure we are doing the right thing. So let me tell you how we'll go about this. Okay, so today in many high-stakes problems, humans are the gold standard, right? In medicine, what treatments are given to patients is decided by humans. In education, teachers decide whether students are at the risk of dropping out. And in criminal justice, it's human judges who are deciding who gets, let's say, let out on bail and who gets kept in jail, right? So the point is that humans today are making these decisions and they are providing the gold standard for us. And the question is, can machines beat the human? And if you think about this, it becomes quite interesting, right? First, in these kinds of settings, humans have information advantage, right? Humans get to see many things that will be very hard to put into features or into some kind of signals that machine can consume. If you think about the doctor talks to the patient, sees the patient, kind of feels the patient, and it will be very hard to quantify that and featureize those signals. On the other hand, we know that humans are biased in many different ways, and that consciously or subconsciously, humans can make suboptimal decisions. So this is kind of at the high level. If you go deeper, it becomes even more interesting, right? So the first issue is this issue of data and features, right? We know today that when human and machine are given the same set of input data, machine beats human. And that's very nicely shown, for example, in any kind of game playing. It's very nicely shown for any kind of image classification, detection of, let's say, cancer from raw images and things like that, right? But if we want to deploy these machines, the problem becomes that when humans make decisions, they have more input data than just this features X. They also have this other data, Z, that is kind of unobservable to the machine. So that's the first issue. The second issue is kind of deeper. This one is about that in many cases, it's impossible to obtain randomly labeled data. Right? What do I mean by that? If you want to train a model for bail decisions, you cannot let out random people and see what happens. Or if you are a doctor and you want to build a model of how doctors make decisions, you cannot, cut into random patients and see what happens to them. Right? So obtaining randomly labeled data is impossible. And what does this mean is if we train our machines on this kind of biased data, this many times will lead in under-reporting of error, and we will deploy bad models while thinking they are working really well. So what I want to do next is I want to go and demonstrate these issues on a particular high-stakes prediction problem, and then talk about how we solve them. Okay, so here's a prediction problem, right? So this problem is called criminal court bail decisions. So the story goes the following, right? Every year, United States police arrests around 12 million people. And after a person is arrested, the question is, where do they wait for trial? Okay, so this is not about whether they are guilty or not. The question is, where do you wait for the trial? And after a person gets arrested, they appear in front of the judge, and the judge effectively decides to release them or not. They kind of sets them a bail amount, and sometimes that amount can be kind of infinite, and sometimes you are free to go. Okay? And if the defendant is let to go, then what can go wrong? There are two things that can go wrong. First is the defendant can fail to appear at the trial. And the second thing that can go wrong is that while defendant is waiting for the trial on the first criminal charge, they get to commit another crime, right? So the question judge is asking is, if I release this person, will they misbehave while being out on bail, right? And what's the point here? The point here is that the judge is basically making a prediction about the future behavior of this defendant. Right? And we know how to make predictions, right? So the idea would be that we would build a predictive model that based on defendants' past criminal activity or history predicts their future behavior, right? So in some sense, we want to build a model that takes in the characteristics of the defendant and predicts whether this defendant will misbehave if let out on bail. So that's the task. Let me give you description of data. So we do this on two different data sets. One is for the state of Kentucky, around 360,000 of these bail decisions. about 73% of the people get released. And out of the people that get released, around 17% of the time something goes wrong. So if you want to think of it, human error rate is 17%, right? The judge's error rate is 17%. This 17% can be broken down as follows. 10% fail to appear at the trial, 4% commit non-violent crime, and about 2.8% commit violent crime. There is also another data set I'll talk about. This is federal pretrial system. Around 1 million of these cases, 78% here get released, and the human error rate is around 19%. So human judges make mistakes in around 20% of the cases. So the first interesting question in this domain is, what features do you use? Right here, even US Constitution tells you what features you should use and which ones you shouldn't, right? So what do I mean by that is that we decided here to only use administrative features. So features that are common across regions, they are easy to get, and there is no way for the defendants to game them. The only way to game them is not to commit crime in the past, which is the way we want kind of criminals to game us, right? So that's the first thing. The second thing is that we only use features that are legal to use. So no race, no gender, no religion. Here I give you some examples of what do we use, like age at the first arrest, time sentenced for residential correction, level of charge, number of active warrants, and so on and so forth. Just basically previous criminal history of the defendant. So now that we have the features, we have the data, we can go train our models, right? So the idea is that now, based on the people that were released, we see who misbehaved and who didn't. We can train a machine learning model. Now we can apply this to some holdout set, where for every defendant we predict their probability of crime if released. I can then sort people by the predicted probability of crime and decide to release the top K with the lowest probability. I could go do that, but there is a huge problem with that. And the problem is what we call selective labeling, right? The point is that our data that we get to train on and we get to evaluate on is not randomly labeled, right? In a sense, judges are almost, in a sense, adversarially hiding the data from us. Why do I mean by that is that when a person is put in jail, we don't get to observe how would they behave if they were released, right? So we only observe the label, the crime, no crime, when the person is actually released to wait for the trial being free, right? And this can really make a big difference, right? If you think about it, we only observe the low green box at the bottom, right? This is the label data we observe. And we can only train our models on that label data. And if we do proper cross-validation and everything, we can only make claims about how well does our model work on the bottom green box of the label data. But kind of we don't care about our performance down there. What we really care about is performance in the real world, which means at the top where we also observe all that unlabeled data, right? And to show you how we could make huge mistakes without knowing, here's a simple example, right? Imagine that judges observe through years of experience that young people who have no tattoos, they commit no crime, okay? So judge learns this rule, observes a young person, says, please roll out your sleeves. Oh, you have no tattoos, you are free to go. Okay, great. So imagine that machine somehow doesn't have access to the tattoo feature, right? So machine will now take the labeled data. These are all the young people without tattoos. They commit no crime. So the machine will conclude that all young people do no crime. So now we go and deploy this machine to replace the human. And basically, this machine will now falsely presume that all young people should be released, and things can go terribly wrong after we have released the model in production, if you want to think of it that way. So the question is, what can we go and do about it? And the solution to this problem is the following. What do we do is the following, and it allows us to compare the performance of the machine compared to the human on this labeled data. And this solution doesn't require any kind of statistical tricks or assumptions. And let me explain how it works. Imagine I take all the defendants and I order them by their probability of crime. Let's assume there is some ground truth ordering to that. And what I can do is I will have multiple judges making decisions. So, some judges will be very strict and some will be very lenient. So what I can do is I can take the release population of a very lenient judge, right? This is this release population, I get to observe the labels. So I can go to apply my machine learning model to this released population and kind of take this lenient judge and make them stricter, right? But now I actually get to observe whether machine learning model made the mistakes or not, right? And based on the release population of now this strict artificial judge, I can now go and compare this to the true human strict judge, and now the comparison is fair. And this way, basically, I can obtain the performance of the machine with respect to the strict human judge. And there are just two conditions needed for this to work. First condition that needs to be satisfied is that cases are randomly assigned to judges. And this is most often the case. So that's an easy one. And the other one is that there is natural variability between human judges, right? That some are stricter, some are less strict. And that's also the case in all the data we looked at, right? So by taking this idea of taking a lenient judge and making them kind of stricter through machine learning and then comparing performance of that strict machine learning judge to the strict human judge, we can compare the performance of the human and the machine. So now I can show you how well this really works, okay? So remember the Kentucky data set. We said that about 73% of the people get released, and out of the released people, around 17% commit crime. So that's the red dot. That's where the humanity in Kentucky, or where the judges in Kentucky are today. So the question is, how well would machine learning do in this case? So here is this contraction curve we can create, right? This is the trade-off between the release rate and the crime rate, right? And we actually get to observe the entire curve because we can do this contraction over all the judges. Now, where is the machine learning here? It's much lower. Actually, if we were to apply machine learning and say, let machines make decisions, and we want to release 73% of the people, the error rate would be about 11%. So that's around 38% drop in the crime rate we could achieve by having the release rate constant. What this allows you to do as well is to say, we are happy with the crime rate, but let's try to release more people. So I can go the other way, and now we could go and release 88% of the people while keeping the crime rate the same as before, right? So it kind of allows us to start reasoning about what's a good threshold where we want to be and where, as a society in terms of the release rate. Another important question here starts to become, why are judges doing so poorly, right? And in some sense, we would think that odds are against the algorithm in this case, right? Judges sees many things that the algorithm does not, right? Here, algorithm just has access to the previous criminal activity, but judge sees the demeanor of the person, right? So the question becomes, can we diagnose the reasons why judges are making mistakes? So we could change training, things like that. So what we developed to do this is we developed like a model that allows us to identify groups of judges that are making similar decisions. So the idea here is that you have judges on the left, you have their decisions on particular defendants. Here, these are little birds, and then you get to, and let's assume we see the true labels. What do we do now is we are able to identify sets of judges and sets of defendants that are judged in a similar way. And what do I mean by similar way is captured by this contingency table or the confusion matrix, where we see the truth versus decision, and the entry in this matrix tells us what's the probability that particular judge decided no crime given the defendant would actually go and commit crime in the future. Right? And we can take our data to go identify what are the groups of judges and the groups of defendants where the decisions or these confusion matrices are consistent. Let me show you a few examples. Here's the first one. So for example, here I'm showing you two clusters, two groups of judges, and I show you the corresponding confusion matrices. The way you would want this confusion matrix to look like is the one on your right, which is you want high probabilities on the diagonal, and you want low probabilities blue type colors of the diagonal. And the cluster on the left corresponds to judges that have a high number of cases, which means judges who are experienced. And the adjacency matrix on the right corresponds to judges who have low number of cases, who are young, who are basically unexperienced. And you see how young judges are making more mistakes than the old judges. This is kind of expected, right? Here is now more interesting observations. The first observation is that, for example, judges who have judged many felony cases in the past, they are stricter. The way you see that is at the bottom row for judges with many felony cases, whenever the truth is no crime, they basically do 50-50. And judges with few felony cases, they do 30-70. So you see how the judges with many felony cases, they are stricter. And here's one that's the last one that's actually quite interesting. These two clusters, one on the left is defendants who are did felonies and moved around a lot, and you see how decisions here are very accurate. But the one where basically everything is almost like 50-50 is a cluster of defendants who have kids, right? So here judges are making lots of mistakes, right? So let me quickly wrap up and conclude, right? So here I kind of wanted to present this framework of thinking about high-stakes machine learning applied to societal problems and really thinking about how could we use machine learning to improve human decision-making, right? And so this is not just about prediction, it's also about making decisions. And everything I said can be applied far beyond the legal domain. You can think about applying this to decisions about patient treatments. You can think about these decisions about promotion process, right? There you also cannot promote random people and then see which decisions were good or not. Hiring decisions is another example. Giving credit or mortgage decisions is another problem, and so on. Right? And in all these cases, what is interesting is that machine models can be used to make this type of high-stakes prediction problems. They can be used to diagnose reasons for bias and really help us improve the decisions. Thinking about this type of problems also raises interesting concerns. Right? The first concern I addressed and talked about is this idea of selective labels, right? Is that it's many times impossible to get random data labeled. So how do we train machine learning models in the presence of biased data, and how can we make claim how well would our models work in this, true data distribution that may be impossible to label. Another interesting question comes when you think about constraints on input features, right? In our case, we cannot use race, gender, religion to classify crime, no crime, right? How do we deal with such additional constraints? How do we make sure that our algorithms are not discriminating? In this particular case, another interesting question arises, which is, I think, new to many applications in machine learning. It is the question of what's truly the objective functions we are trying to optimize, right? Economists would call it this omitted payoff bias, right? In our case, is minimizing the crime rate really what we want, right? And if you remember, I showed you this example where judges do terribly on people with kids, right? You can say judges are making mistakes, or you can say, oh, I would like a judge to make a mistake on someone who has a kid, because putting that person in jail is very detrimental to the family, to the kid, and so on. So maybe there we are willing to take larger risks, right? So the question is, how do we even build machine learning models in these types of cases where objective functions may be unclear? And then the last thing that becomes very important in these types of models is the question of human interpretability and explainability and verifiability of these models, right? How could we vet the model? How could we debug the model in a sense that it doesn't get crazy, on a certain subspace or subpart of the input space, kind of similar to what Percy was saying, right? We don't want our model to make crazy decision on some small subpart of population. And in this part here, we are working actually a lot on interpretable machine learning models and really trying to quantify what interpretability means so we can optimize for it and this way help in this domain and kind of increase trust to machine learning when applied to these high-stakes prediction problems. So with this, I'm done and very happy to take questions. Thank you.
We have time for just one quick question.
So one other question on the interpretability, and I guess that would be transparency, and it may just be because of human preferences or predilections, but if a judge makes a decision, you can imagine appealing it and having another human look at the decision and say, that was a bad decision. We have a tendency to accept when a computer algorithm does something as, well, the computer said it, so you have to do it. So I think there's even a psychological part of your very last slide on interpretability, that we've got to make sure that in these cases, the computer is can't be considered to be perfect, and in fact, that's part of the sales job, is to convince the buyer that the computer is perfect. So you've got a real dichotomy. So I don't know what the question is, but how do you get around the human psychology of what your algorithm is doing as well?
I think there are two questions around interpretability. I think one is to be able to explain your decision. I think that's an easier one. I think a harder one is trying to vet the entire model, right? Like have a model so simple that a human judge can look into it and says, yeah, I think this won't get crazy, or this won't make some very silly decisions at the point later. So I think those are the two. In terms of interaction with humans, actually there have been studies done with judges, and we are actually talking to the courts in New York to actually go deploy these types of tools. And I think my worry there wouldn't be so much that people wouldn't or judges wouldn't trust this. The worry would be that they would trust it too much. Yeah, I agree about that.
Thank you very much, Jure. That was great.
Thank you.